Alright, let's continue with our lecture series. This is a different topic since we have seen all these 25 lectures before. And here we are talking about estimation ideas or observer ideas and all that actually. So, let us see if, to begin with little bit on linear quadratic observer and some sort of an overview of state estimation. I am not talking about detailed derivations and all here, which we will do in next couple of lectures anyway. Okay. But here we will see simply see some fundamental ideas behind this LQ observer, and it also turns out to be some sort of a Kalman filter, whether you realize it or not actually. Okay. But then will also gives much more formalization of this state estimation technique, especially the Kalman filtering ideas in next couple of lectures. However, in this particular lecture we will simply see what the basic ideas and what are the mechanism to operate it and all that actually. So, topics motivation of state estimation, why do we want to do that, then LQ observer and some sort of an overview of state estimation especially using Kalman filter, which is very popular. It works for a lot of problems and things like that. Alright, so this motivation of state estimation first. Why do you want to do state estimation actually? Okay, first thing is for state feedback control design, we really need information about state and hence we need to do state estimation actually. And in practice, all state variables are not available for feedback and possible reasons can be non-availability of sensors are simply not there, or even if they are there, they can be sometimes quite expensive. Okay. For example, a seeker in the missile is typically very expensive. So, unless you are really sure that everything else works, you do not put it there, but you want to have some sort of validation before, on that. So, preliminary launches and all typically are done with respect to radar data, basically, not necessarily with respect to seekers. So, that is the reason the sensor is very expensive, we do not want to kind of just like that use it actually. Sometimes the quality of the sensor is not acceptable because of the noise content, especially if you see this MEMS level sensors which is there, it will give you some data, some information about what is going on, but the information content is very noisy actually. Okay. So, when you have that, obviously you want to use that sensor, okay, or maybe many sensors like that, but then we want to have a filter in the loop which will kind of extract the good information out of it actually. Okay. So, these are some of the reasons why you want to do. So, what is an estimation actually? What is the idea here? A state observer estimates the state variables based on the measurement of some of the output variables as well as the process information. Okay, so, process information means system plant model. It will use that process information as well as the output of the sensors for a finite segment of time actually. Just not at the one instant of time, but sequence of data starts coming. Then from there it will be able to kind of estimate the state in a good way. So, applications of estimation is not just confined to feedback control, it is also you can think about model development, especially parameter estimation and combined state and parameter estimation sort of thing. So, that will be model development, and sometimes you are interested in fault detection and identification. That means, if you estimate the state, you are not doing anything, but simply observing the numbers. And the observation of that number can tell us many things about the status of the plant or status of the system, and then it will also turn out to be that there is something wrong in there, the fault detection actually. For example, probably a nuclear power plant, if you think about temperature control or temperature monitoring rather, if you do, the temperature keeps on rising to some level, then it is probably very dangerous and need to shut down the plant actually that way. So, there is something faulty going on there. Okay. So, that kind of information can be obtained from using this FDI techniques, fault detection identification techniques. Essentially, these are estimation things. And the estimation of states of other related systems to collect exogenous information, and this is the thing that I was talking about. The target information in missile guidance problems is typically done through our own sensor. In other words, target is never going to declare its own position, velocity, intention of maneuver, things like that. It is the missile's job to find out what is going on in the target actually. Okay, so sometimes this exogenous input, which is necessary for computing the command, is done through this estimation actually. So, you can see various applications of estimation thing, and in my view, unless we know something about estimation, the entire control theory is kind of only half explored actually. It may not be complete in itself. So, some ideas of estimation we must have actually. Alright, so LQ observer design first. Let us see what is the idea, and here we do not really require any random variable concepts, and we do not want to go to the filtering ideas in this particular development actually. So, let us talk about some sort of a noise free situation. In other words, system dynamics is known perfectly, and the system variables are also known properly basically. Okay. And the output is also noise free. Then what do you do actually? That is the whole idea here. Okay. So, an observer is a dynamic system whose output, okay, is an estimate of the system vector x. That is the definition actually. So, essentially when you talk about I have got an observer, that what you are telling is we have also got some sort of artificial system dynamics, and that system dynamics output is nothing but the state vector actually. Okay. And then there are ideas of full order observer and reduced order observer. In other words, full order observer tells okay, I will go ahead and find out the entire state all the time. The reduced order observer tells okay, some of the output vectors are actually nothing but the state information, and that output vector does not contain noise. So, I do not want to kind of estimate that, I will just simply take it, and whatever I do not know I will try to estimate that. So, that is called reduced order observer actually. Okay. And also this remember this observability condition must be satisfied for designing an observer. Okay. No matter what you do, observability has to be there actually. Okay. Alright, so let us see this. You have got a linear system plant. Okay. We are talking about linear system dynamics here. So, we have x dot is x plus bu and y is cx. So, motivated by this plant, what you are telling is we also propose an observer dynamic something like this, very similar to what this plant is. Okay, x dot is ax plus bu, it is also x hat dot is a hat x hat plus b hat u plus this ke times y, because y contains the output information. So, we want to put it that way. So, this is our observer dynamics, where the error x tilde is defined as x minus x hat. Okay. Now, the question is what is this a hat and b hat actually, we think that way. Okay. And you can also think okay, these two things you can pictorially represent something like this. This top plant, top portion of the thing is actually nothing but the original system dynamics. X dot is something here, is nothing but a times x plus b times u. Okay, b times u coming here, that is what x dot is, and y is nothing but cx. So, that part is the entire plant, the actual plant, and this plant is the observer. So, you on one hand you have got y tilde, I mean this will be y tilde actually, yeah. Because so there is some notational things with respect to what you are doing. Okay, this is y hat. So, and then there is y basically. So, using this error information, which is nothing but let us say y tilde if you define that way. Okay, then it can be observed. I mean this part of the dotted box what you see here is nothing but the observer dynamics. Okay, this is also x hat in our notation basically. Okay. So, this is what happens there. Now, we talk about error dynamics. So, error dynamics is x tilde, which is x minus x hat. So, x tilde dot is x dot minus x hat dot, x dot is x plus bu, and x hat dot is this expression that we are kind of proposing here. Then we can add and subtract y. Okay, add and subtract this terms a tilde x and substitute y equal to cx actually. Okay. Alright, so we whatever expression we have here, right hand side we add and subtract this term a tilde x and then carry out the algebra like that. So, we have ax, okay, plus bu, which is coming from here, and then this expression is there. So, I mean I am not going to explain all that, it is very clear to you anyway. Once you do that, it turns out that this part of that, okay, is nothing but something like a hat x tilde basically plus this turns into x plus this one actually. Okay. Now, this gives us some ideas actually that what is going on here basically that way. Okay. So, let us go step by step. So, we are talking about this expression first, okay, and this expression. Now, if you look at this this error dynamics x tilde dot, it has to be a function of x tilde only, ideally speaking. In other words, whether x is big or u is big or small, or x is big or small, it should not matter given a choice basically. So, for that reason we want to make the coefficients to be 0. Okay. That means we got an expression for b hat and a hat from here. So, b equal to b hat and a equal to a hat plus k e c basically. Sorry, a hat equal to a minus k e c basically that way. Okay. So, b equal to b hat and a hat equal to a minus k e c. So, now you substitute back, tell that okay, this is my x hat dot, because that is how I started with. Only a hat and b hat was not known. So, now b hat is b and a hat is a minus k e c basically. Okay. So, now I substitute that, and that a minus k e c, this component I will put it somewhere here now actually, and then this particular term y minus c x hat turns out to be something called innovation actually. This is well estimated or predicted output actually, and this is the actual output. So, the difference between that is some new information which is coming to this observer. If the difference is not there, then it is as good as the original plant actually. Okay. And it turns out that necessary and sufficient condition for existence of this gain K E is that the system should be observable actually. Okay. So, the observer design, if you are interested in a full order observer, then order of the observer is same as that of the system of full order observer. That means, all states are estimated irrespective of whether they are measured or not. Okay. So, that is what we are talking about here. Reduced order observers are there, but we are not going to discuss that, because we are slowly interested in Kalman filter really actually. So, we will go ahead and do that way. So, the idea here is to obtain this expression K E. Remember, we have got a structure already. Okay. A and B are known, because that is what the system dynamics is given to us actually. These are typically known things. What is unknown in this entire thing is only K E actually, if you ask me. So, this K E thing is the only thing which you are interested in designing actually, because A, B and C are known to us. Then the question is, how do you do that? Now, here you can see an interesting analogy. We do not have to go through the total thing actually, but the analogy turns out to be something like that. We know the control design philosophy already, and in closed loop control design, this is the system dynamics in closed loop. Okay. Remember, x dot equal to x plus b u and u equal to minus k x. So, that one if you substitute, it turns out to be something like this. Then the objective there was x of t should go to 0. Okay. And that is the whole philosophy based on which we design this k basically. Okay. And we want to extract this benefit out of this thing in observer design actually. We do not want to kind of go back and redo the entire math again. Okay. So, this is the objective here, and in this process we know how to design k basically, either pole placement, what here we are talking about an LQ design. So, we are talking about knowing this k from LQR sort of ideas actually. So, we know how to design this k. Okay. But coming to the aerodynamics in the observer side, this is what we got, x tilde dot, after doing that, x tilde dot is at x tilde, that is all we got actually. Okay. And if you substitute for a, that is what you get. So, if you look at this expression, x dot equal to a minus b k into x, and here it x tilde dot is a minus k is into x tilde. Here the objective was x should go to 0, and here the objective is x tilde should go to 0. It is very similar objectives actually. What you say, have similar system dynamics and similar objectives. Again, I emphasize the word similar because it is not really same. The difference here is this gain k appears in the right hand side here, whereas it appears in the left hand side here. That is the whole difficulty first. But however, it turns out that if you talk about a transpose of any matrix, then the eigenvalues remain same. Eigenvalues of this matrix A minus k e c is same as eigenvalues of A minus k e c transpose. Now, this transpose if you expand, it turns out to be like this, S transpose minus C transpose k e transpose, because this transpose will kind of alter actually. Now, suddenly we got some hope, because k e transpose happens to appear in the right hand side really. Okay. here it was left hand side, sorry, here it was left hand side, we got right hand side, and this right hand side is compatible to what we know in control theory basically. Okay. So, now we go back to the analogy part of it. We have got this is system dynamics, and here was the controllability matrix, here was the observability matrix, and here you constitute a dual system something like that. Okay. A Z dot is A transpose Z plus E transpose V, and output n equal to B transpose Z. Suppose you consider construct something like a dual system here in this form, then you can construct this controllability of this particular dual system and observability of this particular dual system that way. But it turns out that the controllability matrix for the system, original system, is actually observability of the dual system, and observability of the original system happens to be controllability matrix of the original system actually, sorry, dual system. So, here you got the LQR design U equal to minus kx, okay, and that what we want to extract actually. Alright, so control design sense it is x dot equal to a minus p k x. So, objective was x has to go to 0, and we know how to design k in terms of LQR. So, k is nothing but R inverse P transpose P, where P is a positive definite matrix and P is solution of this Riccati equation also basically. Now, looking at that side of the story, we have got this error dynamics, okay, and this transpose is nothing but similar, and something like if you look at a little bit, this k transpose acts like something like a controller gain for this system actually. Okay. So, this k transpose we can actually put the formula here, similar formula k transpose R inverse E P, where this P matrix what you are looking at is designed based on this Riccati equation rather. Okay. Because now you have to remember that A transpose and C transpose are your matrix system matrices actually. So, using that it turns out that this Riccati equation is something like this. Okay. Alright. So, the whole idea here is what it turns out, this is something like filter Riccati equation what you call. So, or observer Riccati equation. So, we solve this Riccati matrix from this equation and then compute Ke transpose like this, and once you compute Ke transpose you can we have got Ke also. And once you got Ke, the observer dynamics is given to us actually. Okay. The observer dynamics we started something like this, right. Okay. So, the whole point was to know Ke, and Ke is now known actually. And remember, we did not go to again the fundamental philosophy of LQR and things like that. We have simply tried to extract it by constructing a dual system. Okay. Alright, so this is your observer dynamics. So, in other words, you start with any initial condition x at 0 and run this system dynamics in parallel in computer only. The only thing that you have to keep on using is y actually. Okay. Everything else is kind of known to us actually. Well, there is a small error again, there is some mismatch of notations from copy and paste sort of thing. So, let me correct this, and this is again this x hat here, okay. Not error, but the observed state actually. Alright, so okay. Now, this is all about Kalman filter in LQ observer in continuous time actually. Okay. Now, moving on to filters, so the whole idea here is we do not get too much of flexibility actually by doing this, because we simply try to take advantage of LQR theory, but what is Q and what is R, that remains kind of kind of filter or observer tuning matrix variables, okay, which we do not get a clue of how to adjust it properly sort of thing. Just but it happens to work actually, that is not a problem. Okay. Alright, now moving on to Kalman filter ideas, which is extension of this ideas and all that. Again, we'll need some sort of random variable concepts and things like that, which we are going to discuss in subsequently basically. But let us see a little bit overview of what is this Kalman filter about actually. Okay. So, main aspect of estimation, if you see, it talks about prediction, filtering and smoothing. So, prediction is what is going to happen in the future, filtering is what is happening right now, and smoothing is what has happened before. Okay. And this typically these three algorithms are based on somewhat similar mathematics, but they have different implications actually. Okay. especially when we have this process noise and measurement noise coming into picture, and some noise characteristics are available to us. Why not using that explicitly? Okay, instead of relying on simply an observer thing which doesn't talk about any noise anywhere actually. That's the whole idea there. So, prediction, filtering and smoothing are the three things. Prediction is what will happen based on what I have observed until now. Using that, can I predict what is going to happen in the future? And obviously, I need a state predictor for that. In other words, a state model for that actually. And filtering is, okay, I have got a sequence of data already, okay, and based on which can I estimate something what is my current state right now. And smoothing is, okay, process is done, but I want to see what has happened before in a much more better sense actually. Okay, there are applications also for smoothing and all, especially when you talk about parameter identification. You go for something like a test flight basically. So, flight is already done, you have got the data already, and come back and try to fit some parameters. So, why not using smoothing ideas? Okay, why should you use only filtering there actually? So, those are the things which you can think about where it is, what is applicable where actually. Okay. And it turns out nicely that this particular formulation of this estimation can also take care in a limited accuracy sense the errors in the system modeling. That means, if you have some sort of system dynamics inaccuracy, you can think that, okay, inaccuracy part of it is nothing but a noise actually. Okay. So, in other words, it can handle that part is kind of much more better sense actually. Especially in structural vibration sense, we typically take about 6th order, some finite order model. Then whatever remains after that is actually noise, but it's, ideally speaking, they are not noise really, because there is a physics which goes behind that. But you can interpret that as a noise for practical applications point of view actually. Okay, so in that sense, it can take care of limited accuracy of limited inaccuracy or errors in the system modeling actually. Okay. So, it can also be used in parameter estimation or system identification. I have already talked about that. Now, if you see history part of it, it goes all the way to way back in 1795, when Gauss first proposed this least square estimation. Okay. And then for a long time nothing happened. People used Gauss least square estimation. Even now it is being used, especially for static optimization ideas and all that way. But then in 1940s, Wiener proposed this new ideas, which is something like filter, and he derived from variational calculus point of view, and unfortunately it requires solution of integral equation, and turns out it is difficult to use in practice. However, the idea content was good, and hence Kalman got interested in that, and he proposed radically. He got quite motivated by these ideas, but he repackaged it in a very different sense, in a time domain sense actually, whereas Wiener filter was in frequency domain largely. Okay, so, and he proposed something which was readily understood, and it actually had recursive solution. So, hence computationally it is very less demanding and things like that. That's why it became quite popular actually. So, around 61 it was a major breakthrough sort of thing in linear estimation theory, and the salient features of that includes recursive solution and suitable for online applications, and subsequently it has been applied in almost all the applications of engineering actually, all domains of engineering. And even though it was primarily developed during Apollo mission, that the moon landing mission actually of NASA, but later it was used for variety of applications, flight control, submarines, GPS, parameter estimation, system identification, automobiles, you can talk about electrical application, robotics, anywhere you think about, Kalman filter has been used actually. Okay. Alright, so this is the little bit history part of it, and again if you revisit the pioneers of optimal control in a historical sense, then something like Bernoulli, Euler, Lagrange comes in 1700 century, but 200 years later all these 1900 giants are something like Pontryagin, Bellman and Kalman. Kalman has done a lot of work in linear systems theory point of view, especially the LQ design of control, LQR theory, or essentially LQ is a linear quadratic design, and various ideas associated with that. using controllability, observability, and things like that. Many things he has proposed, but he is fundamentally known for Kalman filtering actually. So, a little bit on Kalman, just to kind of see historical background sort of thing. He was born on 1930, okay, in Hungary, and obviously now he is 82 plus actually. Immigrated to US in 1943, and around 50, that is where the Second World War was going on actually. That time lot of immigration happened from Europe to US, he was one of that. And then he earned his bachelor's degree in 53 and his master's degree in 54, both from MIT, okay, in electrical engineering. Then he earned his Doctor of Science in 57 from Columbia University in New York City. And then he was actually a research mathematician in something called RIAS, actually, that means Research Institute for Advanced Studies in Baltimore, Maryland, from 58 until 64, and this is where his legendary paper appeared actually. I became then Stanford University professor from 64 to 71, and then he migrated to University of Florida from 71 to 92 he was there, and then from 90, he got slowly associated from 73 onwards with Swiss Federal Institute of Technology, which is famously known as ETH in Zurich, Switzerland. And currently he is an emeritus professor in all the three places, Swiss Federal Institute of Technology again, ETH, and University of Florida, as well as Stanford University, I believe actually. But anyway, so that's the history or background of Kalman. And essentially the Kalman's ideas on filtering were initially met with some skepticism. Well, a lot of people thought this is not a good idea actually, and so much so that his paper was not accepted in IEEE, and he was actually forced to kind of resubmit it and publish it in Journal of Basic Engineering from Mechanical Engineering. That's what it is actually. But he had a lot more success in presenting in ideas while visiting this NASA lab, now it's famously known as NASA Ames Research Center in 1960. This led to the use of filter in Apollo program, and then it followed by Space Shuttle program, Navy submarines, aerospace vehicle, various aerospace unmanned aerospace vehicles, and weapon systems, cruise missiles, and rest is history basically. So, many things were applied after that, many problems actually. During 60s, Kalman was a leader in the development of rigorous theory, and during, it is actually he has proposed many things based on controllability, observability, minimality, realizability, matrix Ricard equation, linear quadratic control, separation principle, various things which are very well path breaking sort of ideas basically. And 70s he played a major role in introducing this algebraic and geometric techniques in study of linear and nonlinear control systems as well actually. And 80s he is focused on little different ideas on economic modeling, identification, and things like that actually. Okay. So, all these information I have taken from Wikipedia rather, okay, and then any of you are interested in this part of this has been taken from this website, okay, and then this is University of North Carolina, and that is where many things are well documented for Kalman filtering actually. Okay. Anyway, about for his pioneering work for various things, he has got several very good medals. First thing is, even though his paper was not published in IEEE, and subsequently he has never published in IEEE also, but finally IEEE gave him the Medal of Honor in 74, and that's IEEE's highest honor. And it has also got a Centennial Medal in 84, where IEEE completed its 100 years. It has kind of honored a few people, and Kalman was one of that. And then there is a Kyoto Prize from Japanese Nobel Prize. It's kind of regarded that way. He has got that also. Then this American Mathematical Society has something called Steele Prize, is the highest prize in that society, he got in 87. And then Richard E. Bellman Control Heritage Award, which American Automatic Control Council gives, that also he has got in 97. And then he has got some Charles Stark Draper Prize in mathematics, from National Academy of Engineers. and that is somewhat considered as equivalent to Nobel Prize, that much of a monetary value as well. And finally, the National Medal of Science from 2000, in 2009 from US, that is typically given by US President actually. So, he has got several very well credit on his soldier, and primarily because of his pioneering contributions. And out of that, the Kalman filtering turns out to be the most well recognized thing actually. Now, I just did a Google search today morning, so that's the day of recording of this lecture today. And if I just go Kalman filtering, that's about something like 20 lakh 90,000 results. If I do Professor R.E. Kalman, it turns out to be something like 8,75,000 results actually. You can see the impact worldwide. Application domains include aerospace, electrical, chemical, mechanical, image processing, robotics, and virtually every field actually. So, that is why it is it's recognized so much actually, and a rich resource can be found in this repository, which is University of North Carolina has a good repository about Kalman filtering. There you can also download his first fundamental basic paper actually. Alright, so let us move on with what is scientific content here. So, the Kalman filter, the information required and task is something like this. So, what is required for operating Kalman filter is something like this. You need to have a system model. We should have a linear model, or rather a linearized model, and then we should have measurements and their statistical behaviors. Okay. And we should have statistical models characterizing the process and measurement noise, and typically they are considered as zero mean uncorrelated white noise. What is that? I will talk about that in subsequent lectures. And then we got initial condition information for the states are also available. That is what we are assuming. That means these are essentially the required information. And using this information, the task is to estimate or filter the state by processing the measurement data and using the system model. Okay. We got a measurement data. Okay, it's various statistics about that. We also have process model. Okay, typically a linear model. So, using that, we are able to. The task is to estimate the states by processing this. Processing means you kind of use in certain formulas or sequence of formulas and things like that, so that you get it estimated state information actually. Again, without any derivations and all, let us see how do we kind of implement it. What is the basic idea here, and what is the final results actually. Okay. So, the system dynamics here we are talking about x dot is ax plus b u plus z times w. Okay. That means, this is like a noise influence matrix sort of thing. Okay. This is control influence matrix B, but this is noise influence matrix. Remember, process noise is a physical noise which is coming and acting on the system dynamics. Okay. So, that is the W of t, which is process noise that acts on the system to disturb the plant actually. And in practice, okay, so if some aircraft is going, there is some gust noise, okay, from atmosphere, that is noise, that's a noise input. If you are driving on the road, the potholes on the road is not very smooth. Okay, so that also is a kind of a noise actually. So, similar things are there for which describes the noise, but that has an impact on the system, and that impact is realized through this noise influence matrix Z basically. Okay. Alright, so that is what W of t is. It is a process noise that acts on the system to disturb the plant. And V of it is measurement noise, and typically it is a sensor noise. Okay, Y is Cx plus V. So, this is the model now, where W and V are noise quantities actually. Now, what you are assuming is W and V has to be zero mean white noise. Okay, again, hold on a second, what it means is white and all that. Okay, so this talks about autocorrelation function being delta basically. That is what autocorrelation function is a delta function, and I will talk about that in next class in a little more detail. But essentially it turns out that if you multiply W of t with W of t1 and W of t2, it turns out to be 0, and V of t1 into V of t2 also turns out to be 0, unless t1 is equal to t2. Okay, so if you talk about the same time instant, then this autocorrelation has some value, otherwise not actually. That called white noise. We also know some initial condition of that is unknown. However, we know some sort of a mean value of the initial condition and some sort of a covariance matrix of the initial condition. What is P naught is okay. So this is if you talk about well x tilde, which is x minus x hat, if you define that way, then P is nothing but expected value of x tilde times x tilde transpose. Remember, this is an outer product, x tilde times x tilde transpose. Okay. That is a matrix actually. So, by definition something like this actually. So, initial condition means you put x 0 here instead of x, and similarly it becomes x 0 tilde times x 0 tilde transpose. So, that is the process noise covariance matrix initial condition. So, that is kind of we are assuming that we know a value. In other words, while mechanizing this we need to put some values for this actually. And W of t, Wt are characterized something like this. W of t is 0 comma q, that means 0 mean, and the covariance is q basically. Okay. So, in other words q, okay, it turns out to be something like expected value of W times W transpose actually. And similarly, R is also expected value of V times V transpose actually. So, these are all outer products actually. So, this is W and V are assumed to be 0 mean, okay, and they have this Q and R are their covariance matrices respectively. Q is assumed to be positive semi definite and R is assumed to be positive definite actually. And also this is also a little bit odd factor. Now, remember R cannot be a positive semi definite matrix. That means whether the sensor is noisy or not, we are assuming that there is certain amount of noise in the system, in the sensor output. Okay, so that is a fundamental fact of Kalman filtering. If you are very sure that the sensor outputs are really noise free, or that noise is something very low, which don't want to kind of account for and all, then you probably go back to the observer ideas instead of relying on the filtering ideas. And filter doesn't normally degrade to observer automatically. That's another difficulty actually. Okay. Anyway, coming back, we are assuming the same estimation or same observer dynamics. X hat dot is x hat plus bu plus k times y minus y hat, where y hat is nothing but expected value of Cx plus V. And then if you expected value being a linear operator, you can separate it out that way, expected value of Cx plus expected value of V. But expected value of V is remember it is a 0 mean noise, that is what you are assuming. So, this is 0 and C is again the expected value is a linear operator. So, C can come out and this turns out to be Cx hat. So, y hat is nothing but Cx hat, okay, even though definition tells that is expected value of Cx plus V. So, you substitute it back and proceed further basically. So, that is what the message here. Okay. Now, what happens is this error covariance matrix P of t is expected value of x tilde times x tilde transpose, where x tilde is that I have already told about that. And it also we also assume that P of t is a measure of uncertainty in the estimate. I mean, why assume? That is the definition actually. Okay, so if you talk about x tilde times x tilde transpose and you take expected value of that, that means it is actually nothing but a measure of uncertainty in the estimated states. Okay. And if the observer dynamics is asymptotically stable, okay, and this case this noise factors W of t and V of t are stationary processes, that means their characteristics do not change, the magnitude keep on, I mean the number of W t and V of t can keep on changing, but their probability density function or probability distributor function does not change with time, PDF actually. Okay. That do not change with time actually. Okay. That is called stationary process. That means the characteristic of noise itself does not change, the value can change. Okay. So, in other words, if the observer dynamics is asymptotically stable and these W of t and V of t are stationary processes, then eventually the error will reach a steady state value. Okay. So, that is what the observation is all about actually. Okay. Now, it turns out that this gain Ke is chosen so that it minimizes that steady state error covariance actually. Okay. So, you have to live with some sort of error steady state value of error covariance, but the idea here is how do I design Ke so that it minimizes not the steady state error covariance thing actually. Okay. And the optimal gain will be some sort of a constant matrix actually. Okay. Now, again how do we design and all I am not going to talk here, but the procedure mechanization of that is something similar. So, we have got initially, we have got this, and Kalman gain is we compute that way, where the P matrix is computed from this algebraic Riccati equation or filter Riccati equation really. Then you operate this observer dynamics this way. Okay. Now, there you can see if you go back to this, okay, let me go back to that. If you see this matrix, okay, there is no G here. Okay. So, but here the filter it will turn out to be G times Q times G transpose. You can see that very quickly here. Okay, G times Q times G transpose. Okay. So, if G happens to be identity sort of thing, then essentially it is nothing but the same LQ observer. Now, the thing is in general it gives us little more freedom compared to just simply an LQ observer. Alright, so the estimator dynamics turns out to be what is given here. Okay, x hat is A x hat plus B u plus A times y minus C x hat. This factor is innovation term. Y is the actual sensor output minus C x hat is the predicted system output actually. Okay. Alright. So, what is the concept of LQG design then? It turns out that okay, you apply LQR method of control design, but X is not available. So, what I do is I will estimate the state and that let me call that as X hat. So, now the control will be U hat equal to minus K times X hat really. So, this will be always available. The problem happens to be in LQ, this is actually called LQG method, linear quadratic Gaussian, where the control happens to be minus K times X hat, and X hat is designed from the filter point of view and K is designed from control point of view basically. Problem turns out to be loss of robustness. There is a separation principle by the way, which tells us that it does not matter, it can be actually done independently and simply you can, in other words, the control and filter design can be done independently and you can simply operate it that way. Okay, nothing bad will happen that way. But the problem happens to be loss of robustness, and the remedy for that happens to be something like LQG LTR designs, linear quadratic Gaussian with loop transfer recovery. Okay. But I will not talk too much on that. Anybody interested can read some appropriate book. Anderson Moore is probably one of the good books for this particular design. Alright, now moving on, what is EKF then? That is a fundamental thing that people keep on using. And when somebody tells you I am using Kalman filter and it does not tell you what kind of filter he is using, what form of Kalman filter he is using, typically by default it means extended Kalman filter actually. Okay. And the whole idea here is nothing but the Kalman filter, but remember Kalman filter assumes a linear model and all. So, this is actually a linear estimator where the linearized system dynamics is obtained about the most current updated value of the estimated state. Okay. That becomes your something like operating point, and from which we will be able to extract this system matrices actually. Motivation for that, for nonlinear system models, Kalman filter is certainly not applicable. So, we want more than that, and then the question is how to predict the state vector and its error covariance. And ECAP is some sort of an extension of Kalman filter via linearization. Okay. And it proposes all available sensor measurements in estimating the value of states of interest, and it uses these three things. It uses the knowledge of the system and sensor dynamics, it uses the statistical models reflecting the uncertainty of the process, process noise and sensor noise, and also it uses some information regarding initial condition. Okay. So, using these things we will be able to compute what is your estimated state. Now, the math turns out to be something like this. X dot is now f of x u plus g times w d, okay, not a x plus b u, it is in general nonlinear actually. And output is also something similar. And typically EKF has various forms, but what is most commonly used is continuous discrete form. In other words, system dynamics is continuous, but the output dynamics is discrete actually. Okay. And again we assume this zero mean white noise sort of thing. So, this happen to be something like this. Okay. and this happens to be something like this. Remember, these notations are very neat because it gives us a mathematical platform to do something actually. So, delta is, this is a direct delta function and this is a chronicle delta function actually. Yes. In other words, if I equal to z, the delta is 1, otherwise I not equal to z, then it is 0 basically. Similarly, if t equal to, if tau equal to t, then its value is 1, and if it is not there, anything different, the value is 0 actually. Okay. Alright, so it essentially we are talking about is continuous discrete form of EKF, and where the system dynamics is continuous with noise input of course. The output dynamics is discrete with its sensor noise, sensor noise intact basically. So, it works in two steps. First thing is time update, that means it talks about prediction and then correction. Okay. So, whatever is the current estimate, you predict for what will happen in the future, but whenever the data comes in, that point of time you tell, okay, it is time for correction, and hence you do some sort of corrective steps actually. Okay. So, how do you predict from tk minus 1 plus to tk minus is, okay, what is tk plus minus and all that, which really is something like this. Suppose you have got t and this is got tk, it is a tk plus 1, sorry, tk minus 1, and this is tk and this is tk plus 1, let us say. Okay. So, you got something, you predict it here. So, this is called tk minus, this is tk minus 1 plus. Then you update here from here to there somewhere, and then you predict actually. So, this is nothing but tk plus, and this is nothing but tk minus tk plus 1, okay, minus. Then again it will be updated, okay, then again it will go like that actually. So, this is the notation here. So, how do you do the prediction from tk minus 1 plus to tk minus? Okay, this path what you are seeing here, how do you do that actually? So, that is done by simply propagating the state equation without noise. So, you construct a state equation without noise, okay, and simply if you know this value, you can propagate to that. Okay. Then you, along with that, you also propagate the error covariance matrix P of t this way. Okay. So, where it will come and all we will discuss later. But then you use this equation P dot of t is nothing but P A plus I transpose plus Q, where A t is given defined as del f by del x about x hat, that is more important. So, linearization is carried out at the most estimated current value of state, that is what of AT, that is what it means by A of t basically. Okay. Alright. Now, compute the filter gains, that means KEK is something like PK minus CK and things like that. This is again how it comes in all we will talk later. But once you get TK minus, it is time to update to TK plus also. So, that TK that is done that way. KEK you compute this entire expression, where CK minus is computed at that actually, okay, because you have already come here. So, whatever CK minus is there, you compute using that expression. And then you update the state and stated error covariance matrix this way. So, x at k plus turns out to be something like this, where pk plus turns out to be something like this actually. There are different expressions for that as well. Yeah. Alright, so advantage is, first of all, it works for a wide variety of practical problems and it is computationally very efficient, but limitations are also there, and some of them are something like linearization can introduce significant error and hence EKF may not work very well. No general convergence guarantee, I mean it works we know, but convergence guarantee sense theoretical proof is probably not there. And then it works in general, but in some cases the performance can be very bad actually. So, it to be slightly careful about that. And it also turns out to be a kind of unreliable for color noise. The color noise is something that is not really white. Okay, in other words, the self correlation is not, autocorrelation is not a delta function. Then what actually? Okay. And then there are issues something like this. How do you kind of optimize, even if kernel EKF works, there are issues like this. Okay. So, how do you optimally place the measurement schedule basically? So, when do you measure it? What is the optimal sequence actually? That we do not know. that is a tuning issue of course. Then parameter or modeling uncertainty, if the you are relying on some sort of a model to predict the behavior, but if the model itself is wrong, then what do you do actually? Then there are issues of computational errors, then there are issues of noise model. Okay. In other words, if the noise model turns out to be non-Gaussian PDF, then what do you do actually? Okay. So, these are some of the issues, because of which there is a need for going beyond EKF. Okay. And here we talk about the need being nonlinear systems, typically systems are nonlinear. We have got this non-Gaussian noise or inputs. We got this correlated noise also, okay, uncorrelated and correlated. Okay, what you talk is self correlation and all, what or autocorrelation, but there is something also called cross correlation. Okay, again we will talk about that in subsequent lectures. So, cross correlation means if I take x1 of t1 and x2 of t1 again the same time, but two different values, then if I take multiplication of that, it also turns out to be 0 actually. Okay. But in general it is not so, one has an impact on the other and things like that. So, in that particular case what will you do? So, that is called uncorrelated noise. And typically there are many filters which have been proposed beyond EKF. The very first thing that comes to mind is something like linear regression EKF, linear regression Kalman filter, or something very popularly known as UKF, uncentered Kalman filter actually. So, then people talk about H infinity filter, then there are ideas of particle filter and things like that actually. And characteristics of such filters are typically they are often approximate, okay, and they sacrifice theoretical accuracy in favor of practical constraints and considerations, okay, like something like robustness, adaptation, numerical feasibility, all sort of things they will talk about, but then you have to sacrifice theoretical accuracy a little bit there. So, essentially the attempts are there to cover the limitations of EKF, that is the fundamental idea actually. But here you are in this particular course we will not talk anything beyond EKF, okay, we will see whether UKF can be kind of discussed here, but essentially we talk about EKF in general, then we will see whether UKF ideas can be brought in. But more than that we will not be able to discuss, it is not necessary also, many times UKF or maximum UKF will do the job. And remember particle filtering and all are nice, the many things you can do that way, but your computational demand turns out to be much more than EKF actually. Okay. UKF and EKF is not too much order of magnitude difference, this will be a little bit more, but not in order of magnitude difference. However, particle filters and all will demand lot of computational time actually. Okay. But essentially all of them try to kind of cover the limitations of EKF. Okay. So, that is what it is. Alright, I think this is all I want to talk about. Next lectures onwards we will see various derivations, theoretical foundations and all for Kalman filtering. Thank you.